Hi Ironman, this is your recap video. Sorry it's a few days late. What we covered on Friday and Saturday was what I call the big six. Yeah, so we did a revision of all those techniques of differentiation. Essentially, more complicated functions than you're used to using. So you're very much used to doing the polynomial stuff, bringing the power down, taking one off the power when you differentiate, and when you integrate, adding one to the power and dividing by the new power. But what if it's more complicated than that? What if we have a combination of things? So we have three techniques for each, three techniques for differentiation, three techniques for integration. So we're going to go through all those: chain rule, product rule, quotient rule, integration by substitution, integration by parts, and derivative division, which hopefully makes sense. And I put in brackets the chain rule because actually it's just a chain rule in reverse for a very specific example. But also I put division there to say the only real way that you can do a division, integrate a division at A level, is in this way. So we'll have a look at that now. So first of all, chain rule. So the thing we're trying to differentiate here is what type of function. I've asked you a million times, so you probably say straight away that it is composite. Yeah, so here's some examples of composites I've just written randomly around: sine 2x, e to 3x, log 7x. Sine x is also a composite function because x is a function and sine of x is acting on that function x. Remember, we don't think of it like that because it's not got a number in front of it, but it's still got an x in it. X is a function, so sine x is a composite. Well, we just do, because we've got two functions, differentiate 3x, it's 3x there. We're going to differentiate, and we're going to differentiate e to the whatever that e to the is, it's going to be the same thing again. So now we times the two together, so it's just going to be 3 times by e to the whatever, in this case 3x. The answer is 3 e to the 3x. And sometimes when it's that simple, we can just write the answer down by inspection. You don't have to write all the working out. Okay, so in an exam situation, if you're particularly hurried, you could just put by inspection. That's fine, that is acceptable. You don't have to put all the work in. So with the chain rule. Next up we have the see if it's a bit neater. It is slightly. So let me know what you think of it anyway. Product rules, two different kinds of functions really. If there's just multiply them together to the x, we could then have a polynomial x times by an exponential e to the x. I've got to use the product rule for that, and that is of course v du plus u dv. Hopefully you remember that comes from multiplying the of u plus du times v plus dv, and that comes out uv, but we take that away because we're not interested in that. Just the change will be v du plus u dv. And then we just find v is e to the x. Du is going to be derivative of x, which is 1, and to the x, that unique function we talked. It's the only function where when you differentiate it you get the same thing, but also the y coordinate of every value is the same as it shares its gradient. So when x equals 1, y equals location coordinate. So a very interesting and unique function. So what do we get? E to the x, because it's e to the x times y du, which is 1, plus x e to the x, because it's u x times by dv, e to the x. And then I factorise that at the end. So e to the x brackets 1 plus x. And that's the product rule. So division, and x over sine x is what we're looking at here. We've got u on top, v on the bottom. So u is x, v is sine x, du will be 1, dv is cos x. This time it's v du minus, because division and subtraction, u dv. So v squared, and I don't know if you remember where that comes from, but I sent you the working for it, and we haven't talked through it yet. When we come to do the binomial expansion in more depth, I'll tell where it comes from. So we just use that formula and stick it all in. We've got uv, dv, du, and dv. Put them all sine x times. Next up is integration. So the three integration techniques are just this one actually. So we're going to integrate composite functions like we differentiate using the chain rule. So sine 2x. So here u equals 2x. So dx must be by 2. So I'm going to replace 2x with u. I'm going to replace dx with du over 2. So that's what I've done on the right hand side here. I've put the half outside of the integral. It doesn't actually matter where I put it, but it's more neat to put it outside, and that's because it's not going to have any effect on the answer. Then I'm going to integrate sine u, well that's minus cos u plus c, divide by 2 because of the half, and then I'm going to put the the u back in, which is 2x, so it's minus cos 2x over 2 plus c. Remember to put the c. Second technique, probably this time we're integrating them, so here we're going to use integration by parts. Just to put u, v, v du, u dv, integrate that whole thing, you're going to get the same, got the same thing, the same people. Vectors, I suppose, turn up u, v, v du, u dv, but with some integral signs on there, and it's slightly, the trick of it is that we reorder it, minus v du. So I can just figure out what they are, I can find the integral. So there are e to the x is dv, so I've replaced x and dv with e to the x. From there, du is 1, is 1. The x, the integral of that is e to the x as well. So then we just stick them into the right hand side. So uv is x e to the x minus the integral of v du e to the x. Integrate the right hand side. So that's just, and then I've just factorised our answer there. So e to the x, x minus 1. Okay, there we go. So that next up, this division integral. So what we need for this specific derivative function is the numerator. So the derivative of tan x is sec squared, and look, there you go. If you integrate that, we just get log of whatever this is. Okay, and that's it. That's a general. It's the only kind of integration with a division in it that you do at A level. Reason for that is the integral division is quite possible situations, and as a result, as mathematicians, which we've got an advanced maths book, page 1 literally would be a table of all the values. I'll send you a picture to prove that. So below that, I'm just explaining why it's the reverse of the chain rules, because you might think, well, how not the reverse of the chain rule? That's true. It uses the same idea, but what they have in, okay, they're both using the chain rule, but in particular this is for divisions only. So if I now differentiate my answer here, log tan x, I just ignore the c, it's going to become 1. It's going to become 0 even. That's a composite function, isn't it? Log of tan x. So I'm going to need a chain rule for that. So u equals tan x, dx is sec squared. That makes y equal log u, because I put the u in there. dy by du is 1 over u, because of 1 over. And we'll multiply them together for dy by dx, and that's going to give me sec squared times by 1 over u, 1 over tan x. So I get sec squared over tan x, which is what I started off with here. So actually this technique is a reverse the chain rule as well. It's just that it's a specific one with the division in it. Okay, that was quite quick run through, but it's stuff that we've already done and you're becoming more familiar with. The key thing is to get very skilled at those 6, because the thing is that you won't be told what to do. You won't be told to use the quotient rule or use integration by parts. You might be, but you're better off taking it that you won't be. So you need to learn to recognise which one to use, because you've got 6 different things to use, and you have to learn which ones to use for yourself. It's a bit like trigonometry, where you don't know whether to use sine, cos or tan. You need to learn for yourself which one you should use by figuring it out, becoming familiar, just gaining fluency. Okay, so I'll speak to you on Wednesday. Again, give me your feedback on the video, anything I've not mentioned, anything I should mention, anything you'd like to see, and I'll speak to you then.